This video contains the solutions for 27 through 29 in your AP Physics practice test. Some more relatively tricky problems here, I think. Number 27, we have a stone falling from rest from the top of a building as shown above. Which of the following graphs best represents the stone's angular momentum L about the point P as a function of time? Well, we saw an example problem just like this in the book. It was a penguin falling, I think, in our book. And remember that angular momentum is, what we said, L, is R cross P when we consider these to be vectors, right? But one way of getting, making this a little simpler is this is R cross, of course, that's M, V. Those are the vectors, right? And that's R, M, V sine theta if you want to get rid of the vectors, right? That's how we find the magnitude of a cross product. And the way of getting around that was if you know either the perpendicular component of R, and perpendicular to what? Perpendicular to the other vector. You could do that, or you could do RMV, that perpendicular one, right? That's a little way of getting out of that, or getting around that, making it a little easier. And in our picture here, the distance R, although that's changing, since velocity is straight down, the component of R that's perpendicular to the V is constant. So angular momentum is, this is the one that we're going to do, R, the perpendicular, times the mass, times velocity, and these are constant. So that means a graph of angular velocity, of angular momentum is going to look like a graph of velocity. And what would the velocity of this look like? Well, the only force acting on it is gravity, so it would have a constant acceleration. And that looks like C. So that's a little tricky, but we did see a problem like that earlier in the year. And that idea that something falling, its angular momentum about a point, is looks very much like a velocity graph. It's linear. Number 28, we have a non-linear spring. If it were linear, then force would equal kx. And this is not linear. You can see this looks cubic. That's 1 cubed, 2 cubed, 3 cubed, and 4 cubed. So it looks like, in fact, if you wanted to write relationship, it's not force equals kx. And remember, if you ignore the directions like they often do, you might be wondering why there's no negative sign. They're just taking the magnitudes of these things and ignoring direction. So that's not happening here. What is happening is force is equal to x cubed. I think that you just have to kind of look at those numbers and recognize that these are the perfect cubes. See that relationship. Hopefully you can spot that. So let's see. Especially design spring is stretched from equilibrium to the distances here and the restoring force here. So we write down that relationship. What's the potential energy of the spring when it's stretched 3 meters from equilibrium? Well, remember, work and energy are equal to each other. So work equal to energy, and work, remember, is the integral of force. Work equals force times distance, right? But if the force isn't constant, then we have to do an area trick there. And since we're talking about force times distance, it has to be dx, right? The integral of force as a function of time is equal to the change in momentum, right? That's impulse. This is work. Really important to keep those clear. And hey, I've got that right here. So let's see. As I stretch the spring from 0 to 3, the force is x cubed. So that's x to the 4th over 4 from 0 to 3, and that's 3 to the 4th, sorry, is 81 over 4 minus 0. So that's answer choice C, 81 over 4 joules. And number 29, let's let's see what you know about springs, or simple harmonic motion, I should say. So an object, it is a spring. An object on the end of a spring with spring constant k moves in simple harmonic motion with amplitude a and frequency f. Well, let's see, frequency f. Period is equal to 1 over f, right? And period is also equal to 2 pi times the square root of m over k. So let's just keep those relationships in mind as we move forward here. The simple harmonic motion is described by, you can use sine or cosine. I'm going to do it like we did in class. It would be a, that's its amplitude, times the sine of, and then this is the period, right? So that would be this. Or remember the number that goes in here, like since the beginning of when you studied trig functions, this is 2 pi divided by the period. Well, f is the, since f is 1 over the period, this is, if you want to divide by the period, that would be 2 pi divided by t would be the same as 2 pi f. And there's no times time, right? There's no big mystery. Like the inside of these are all, they all have 2 pi ft in them, so that's got to be that. But that's why, because frequency is equal to 1 over period, and what goes in here? 2 pi divided by the period, and that's the same as 2 pi f. So what's the derivative of that? We're trying to find kinetic energy, right? So that's why I'm trying to move toward velocity. That would be, velocity as a function of time is equal to a times, this is 2 pi f, that's the derivative of what's inside, times the cosine of 2 pi f t. And kinetic energy would be equal to 1/2 mass times velocity, that's this expression, squared. It would be a squared times, well here I think is where maybe we want to find some kind of expression for f. F is the same as 1 over t, so I think maybe, let me just, over here on the side, and that means that f is 1 over t, so that'd be like 1 over 2 pi times the square root of k over m, right? I flipped everything over. So let's see, this piece right here would be, you know what, I'm going to square the whole velocity so I don't get mixed up here, so I'm not going to square the a right now. 2 pi over 2 pi, that 2 pi and this 2 pi cancel out, and the f, so I just have the square root of k over m here. See that substitution there? And cosine of 2 pi t, that whole thing squared, that's going to be 1/2 m, and then I'll square everything now. So that's a squared times k over m times cosine squared of 2 pi ft. The m's cancel out, and that looks like answer choice B. 1/2 k a squared cosine squared. So that's where the m went. The m ended up canceling out there. So important things to know in that situation, that you can start from here. You need to know what the period is and the relationship between period and frequency. So I think that's a relatively tricky problem. But you know anyway, I think, even if you're guessing, that since kinetic energy is 1/2 mv squared, that you're probably looking at something that has those squares in them, and that would eliminate these 3 answers. So you'd at least have a 50-50 shot there. And hey, it's 1/2 mv squared, so look, there's the 1/2. Come on.